So we will be discussing one more problem on the design of squirrel cage rotor. Design a cage rotor for a 40 HP 3-phase 400 volt 50 Hz 6 pole delta connected induction motor having a full load efficiency of 87% and a full load power factor of 0.85. Take D is equal to 33 centimeter and L is equal to 17 centimeter. Stator slots equal to 54. Conductors per slot is equal to 14. Assume suitably the missing data if any. So the data given in the question are listed out here. The machine is a 3-phase one. The output power rating in HP is 40. The voltage is 400, 50 Hz frequency. The machine is having 6 poles and the stator is delta connected. Efficiency is 0.87, power factor 0.85. The number of stator slots equal to 54 and the number of conductors per slot is 14. Each slot contains 14 conductors. The main dimensions D and L are also given. The diameter of the stator bore is 33 centimeter and L is equal to 17 centimeter. The length of stator core is 17 centimeter. D and L are the dimensions of the stator, the diameter as well as the length of the stator. Okay. So we have to design a cage rotor. Okay. So it is as to design a cage rotor. So if we have to design a squirrel cage rotor, what all things we have to calculate or we have to find out? So first of all, we have to fix the number of rotor slots, SR. Then we have to calculate the rotor bar current. Then the area of cross section of the rotor bar. Then we have to design the end ring also. The current flowing through the end ring, the area of cross section of the end ring. And we can also calculate the diameter of the rotor as well as its length, the rotor core length. So we will be finding out all these parameters related to this squirrel cage rotor. Okay, first of all, let us see how to fix the number of rotor slots. So we already studied certain rules regarding the selection of number of rotor slots in a squirrel cage rotor. So we have studied 4 rules and we have summarized the points specified by each. And by that we know that the difference between stator slots and rotor slots cannot be equal to 0, plus or minus p, plus or minus 2p, plus or minus 3p, plus or minus 5p, plus or minus 1, plus or minus 2, plus or minus p, plus or minus 1 and plus or minus p, plus or minus 2. Okay, so here we have the value of p, the number of poles, 6. So substitute the value of 6 and find out the value SS minus SR cannot have. Okay, so 0, initially 0, then plus or minus p, p is 6. So SS minus SR, difference between stator slots cannot be plus or minus 6. Then 2 times p, 2 into 6, 12. 3 times p, plus or minus 18. Then plus or minus 5 times p, 5 into 6, 30, plus or minus 30. Then plus or minus 1, plus or minus 2, plus or minus p, plus or minus 1. P plus 1, 6 plus 1 is 7. So it cannot be plus or minus 7. 6 minus 1 is 6 minus 1 is 5. So also it cannot be plus or minus 5, which is not indicated here. This value is actually plus or minus 5. So this is not plus or minus 6. This value is actually plus or minus 5. Okay, now plus or minus p plus or minus 2. So p plus 2 is 6 plus 2 8, so plus or minus 8. Then p minus 2, 6 minus 4, that is plus or minus 4. So SS minus SR cannot be 0 plus or minus 6 plus or minus 12 plus or minus 18 plus or minus 30 plus or minus 1 plus or minus 2 plus or minus 7 plus or minus 5 plus or minus 8 and plus or minus 4. Okay. So SS minus SR cannot be equal to these values. So from this we can say that the value that SS minus SR can be is plus or minus 3. It cannot be 0, 1 or 2. Then it can be plus or minus 3. And this is the value which is commonly used to fix the value of rotor's loads. SS minus SR can be plus or minus 3. So we can take SR as SS plus 3 or SS minus 3. Okay, the number of rotor's load can be the number of stator's load plus 3 or number of rotor's loads minus 3. So we have to remember this value. So this is the usually used value to fix the number of rotor's loads in a squirrel cage rotor. Okay, so here in this particular case we will be considering the number of rotor's loads as number of stator's loads minus 3, that is 54 minus 3. Number of stator's loads is given as 54. So rotor's loads equal to 54 minus 3 is equal to 51. Okay, so we have fixed the number of rotor's loads. Now we have to design the rotor bar. So first of all we have to calculate the rotor bar current, and we know the equation for rotor bar current, that is 0.85 into 6 into TS into IS divided by SR. So we already know the value of SR. We have fixed it as 51. Okay. So now we need to calculate IS and TS. So or 6 TS. We know that 6 TS is the total number of rotor conductors. Sorry, total number of stator conductors. So here it is given that the stator is having 54 slots and each of the slot contains 14 conductors. So we can calculate total number of stator conductors as 54 into 14. So total number of stator conductor is 54 into 40. So instead of 6 TS, we can substitute this value 54 into 14. We need not calculate the value of TS and then multiply it by 6. We can simply substitute 6 TS as 54 into 14. Okay. Now we have to calculate the stator current per phase, that is IS. Okay. So it should be calculated from the stator current is the stator is at the input side. Then stator current should be calculated from the input power rating, input kVA or input apparent power rating. So what we have is the output rating in HP. So the output power rating in HP into 0.746 gives output power in kVA divided by, sorry, not in kVA, in kilowatt. 40 HP into 0.746 gives the output power in kilowatt, and that value divided by the efficiency gives the input power in kilowatt, and kilowatt power in kilowatt divided by the power factor cos phi gives the power in kVA. So here input kVA is calculated as output kilowatt rating divided by efficiency into power factor. Okay. So 40.351 is the input kVA rating. So we know that input kVA is equal to 3 into V phase into I phase into 10 raised to minus 3, or root 3 into VL into IL into 10 raised to minus 3. Okay. Or we can write 40 kVA. 40 kVA is what? 40 into 10 raised to 3 volt ampere. 40.35 into 10 raised to 3 volt ampere. So which is equal to 3 into V phase into I phase. 40.35 into 10 raised to 3 is equal to 3 into V phase into I phase, equal to okay, this is how we can calculate the value of stator current per phase. So stator current per phase is equal to this value Q divided by 3 into V phase into I phase. Okay, 40.35 into 10 raised to 3 divided by 3 into V phase into I phase. Here the voltage given is 400 volt, which is the line value, and we need the phase value of voltage here. So here it is given that the stator is delta connected, hence line voltage and phase voltage are the same. So we can substitute 400 here. Okay, so we will get the value of stator current per phase as 33.62 amperes. Okay, so which is the stator current per phase IS. So we got the value of 60S and IS. SR we have fixed as 51. Substituting all the values, we will get the value of rotor bar current as 423.6 amperes. Now we need to calculate the area of cross section of the rotor bar, which is equal to current divided by current density. Current in the rotor bar divided by current density of the bar. So current density is not given here, but in theory we have studied that the current density can vary between 4 to 7 ampere per millimeter square. So let us assume the current density as 4 ampere per millimeter square. So current by current density gives the area of cross section of the rotor bar. So as we are substituting current density in ampere per millimeter square, the obtained area will be in millimeter square. Okay. Now we have to design the end ring. For that we have to calculate end ring current as well as the area of cross section of the end ring. So end ring current is SR into IB divided by pi P. Okay, we know the value of SR. We have also calculated IB, and number of poles is 6. So we will get end ring current as 1146.139 amperes. For end ring also we can assume the current density as 4 ampere per millimeter square, and current by current density gives area of cross section of the end ring as 286.53 mm square. Okay, so now we have almost designed the squirrel cage rotor. Now let us find out the diameter of the rotor as well as the length of rotor core. Okay, so this outer section here in this diagram, this outer section is the stator. Okay, this is the outer periphery of the stator, and this is the inner periphery of the stator, and this one is our rotor. And we know that, see, let us draw it. Okay, if this is the rotor, then this will be the air gap. So this will be length of air gap LG. This is LG, and this is also LG. Okay, in between the rotor and stator there is the air gap. So this is also LG, and we know that this is our rotor, and this is the rotor diameter dr. Okay, let us denote the rotor diameter as dr. Okay, and see this one, this is the diameter of the stator, which we denoted as D, capital D, the main dimension, capital D. So this is capital D. So we know the value of D, then what will be the value of dr? From this diagram we can see that D, the diameter, inner diameter of the stator, is equal to dr, diameter of the rotor, plus 2 Lg. Dr plus 2 times Lg. Okay, so this is the diameter of the stator. So then we can calculate the diameter of the rotor as stator diameter d minus 2lg. Okay. So dr rotor diameter is stator diameter minus 2lg. Okay. So then we can find out the diameter of the rotor and also the length. Length of the rotor core can be simply taken as equal to the length of the stator core. So which is given as 17 centimeter. So length of rotor core is equal to length of stator core, that is 17 centimeter. Now we can calculate the rotor diameter dr as stator diameter minus 2 times the length of air gap. So for that we need to calculate the length of air gap Lg. Okay. So there is a formula for calculating the length of air gap in induction machines, that is 0.2 plus 2 into square root of dl, where d and l are the dimensions of the main dimensions, the stator bore diameter and the length of stator core, so which are already given as 0.33 meter and 0.17 meter. Okay. So we have to substitute d and l in meter. In this particular equation, d and l should be substituted in meters and the answer will be in mm. Okay. So the answer is 0.7 mm. So substituting the value of air gap here, we will get the value of rotor diameter, which is equal to 0.3286 meter. So thus we have designed a cage rotor for this particular induction machine.